Thanks a lot for inviting me. So as we were discussing with the chairs, I come more or less from the community of MICAI, where I was in the board for about 10 years, and I'm a fellow there, so I'm coming from there. I know that many of you have interaction with MICAI. So I try to first talk about what we do. So we were actually, my team, so we are about 80. About 65, 17 in TU Munich, and about 15 at Johns Hopkins in Baltimore. And we are working on a lot of subjects, but most of the reason is that I'm interested in computer-aided medical procedures, but in particular in computer-assisted interventions. And originally we started maybe about 8 years ago, 9 years ago, to have a lot of AI in our computer vision section or group and in our medical image analysis, but very quickly AI is now used in everything we do, basically is a main component. So since we do a lot of things, these are all different pictures of what we do in the lab. In our labs, actually, just to let you know, are at the hospital. So we have one lab at Rechter Isar in the center of the Munich, and the other one at the hospital on the other side of the river in Munich, which is in Nussbaumstraße with LMU and TU both. And at Johns Hopkins, we work with a series of surgeons. So before getting to pure AI for diagnostics, since I'm really fond of intervention, and I know you do vascular, even though most of the work I see that you do here, a lot of it also including angio and MRA, but most of them are focused on diagnostic, I would say. Our focus has been always on intervention. So I show you a little bit of applications. In most of them, AI now is used, even though it originally was not. And then at the end, maybe during the second half of the talk, I will try to focus on actually the AI part of what we do. So in angio, what we were doing for many years together with Siemens Angiography in Forsheim, they were sponsoring us to do registration of preoperative CTA that you see on the left-hand side. Of course, it can be also MRA, and angio, interventional angio. And these were source of about 5 PhDs at that time, doing motion compensation, doing a lot of things. So we were doing CTA followed by vessel segmentation, contrast injection, digital subtracted angiography, rigid and deformable 2D, 3D registration then. Then we were doing motion compensation. Oh, what happened? To show you very quickly is that a few years ago when I went to Johns Hopkins in 2011, I met a professor who was working on fish. This was the break to my visit, where they told me, if you want to have a break, talk to someone who does not work on medical. So he was doing, this is Noah Cohen, he was looking at electric fishes who in South America, they send electrical signals out of their body and then they measure their environment. So once I saw that, I thought, okay, we can send these fishes inside the body of the patient and replace this whole part of doing contrast injection, digital subtraction, rigid deformer registration, motion compensation, catheter segmentation, catheter shape estimation, catheter tracking, mapping of DSA. So these things are about 7 TMI papers that we have published, but I think all of them can become replaced by bioelectric localization. And what do I mean by that? So basically, is to change the process and not use X-ray at all. Maybe if we start with MRA, then we don't need X-ray at all during the whole process. So this was the Nature paper originally about the fishes. And what we did, we replaced these fishes with a catheter, which also does the same thing as fishes. So it sends electric signals, low voltage out, and measures it. And by measuring that, it's measuring the impedance, and that impedance dramatically changes if you come to a bifurcation. So which means that if I move what you see on the right-hand side, if I move the catheter And if I have a segmentation of what you have seen on the right-hand side, then I can show what I call a Pac-Man visualization. Only based on the signal, electric signals, I can localize where the catheter is during the operation. So basically the whole process is that you do MRA or CTA, you segment your vessel, you simulate the signals that you're expecting based on the impedance, which is mostly based on the size or diameter or variation of the diameter of your vasculatures. And during the process, you just measure this impedance inside the vessel. No need to x-rays or imaging. And what you will see here as an example is that as you come in, you start eliminating options, and you end up matching in which branch and where in the vasculature you are. So some of our vascular surgeons got really excited. One of the most excited one was actually Dr. Gottby from in Pasing in Munich. And then he allowed us together go to pig studies. And basically he was super excited because in fact we were able to localize. This was chose the x-rays only for validation. So we were able to localize, I hope the video runs. Yeah, we were able to localize all the bifurcation. So you see when I arrive to this bifurcation, you see a peak in the impedance over there. And you can actually localize where you are theoretically with no x-ray. So this was just something to show you, which I'm hoping in future would replace our angiography with x-ray during the operation. But we also do a lot of robotics, and we combine, in this case, this is for measurement of aorta. We take a preoperative MR, not in this case for the patient, but just an atlas. Then the surgeon tells us which area, or the diagnostic radiologist tells us which area they are interested in order to do the measurement, or what do they want to measure. Then the system automatically goes on the patient. We have done over 50 volunteers in this case, and 4 actual patients on spine. The system does a volume. There is a 3D camera on top of the patient. That's why you saw the 3D reconstruction. Then we do a 3D volume. Then we do a deformable registration to the MR, to the atlas of MR. And that enables us to measure whatever we wanted to measure automatically. And then, instead of, again, an alternative to angiography, in this case, the robot would servo automatically follow the catheter within the body. So this was based on localization in the preoperative CT and what we call ultrasound servoing, where the robot, as you enter the catheter, the robot automatically tracks, the robot with the ultrasound automatically tracks the catheter. So again, another way of bypassing the X-ray. So the system automatically follows the catheter within the body in order to do the matching between where the catheter is and this is very, very recent. It will be presented in Macau, in IROS in October. So basically, these were a set of applications where in all of them at some point AI is used, but mostly we are looking at A to Z solutions. Another place where for us, again, artificial intelligence and machine learning plays an important role. Many people who know me, they know me mostly because of the work we did in the last 20 years on medical augmented reality. And one of the things we had done was systematic, this was when I was at Siemens 20 years ago, systematic imaging of video and X-ray in the same system. And what we were getting was a combination of the two. However, with machine learning, what we can do is that what we got originally and went to 40 patients was an automatic acquisition of X-ray and optic, what you see on the left-hand side. But thanks to machine learning, what we can do is that in each of the two images, in optics and X-ray, we can recognize or segment each of the anatomical objects or objects in the scene, whether it's in the video or in the X-ray for every pixel. And then we can decide intelligent fusion based on the relevance we need inside the operating room. So basically, you go from the left-hand side to the right-hand side with the same two images. As soon as I show this to our head of nuclear medicine, Professor Schweiger, in Rechter Izar, he was telling, why am I looking at PET-CT or PET-MR in a messy image where there is a lot of uptakes that covers area of interest in MR? Can we do an intelligent also fusion or visualization of MR PET or or PET CT, where only the relevance objects from each modality are highlighted? And this is the way to go, basically based on machine learning, to select for every pixel in each modality what would be the factor of opacity you want to have for that to have a correct fusion. The last application I show before I go really to AI is again at Johns Hopkins with these two unbelievable surgeons, Alex Johnson on the right-hand side and Dr. Osgood, Greg Osgood on the left. These surgeons are some of the only surgeons I know in my life that in the last 4 years they are doing almost every surgery with head-mounted display. They got ethical approval about 4 years ago to use head-mounted displays, and they are using them not to superimpose data on the patient, but to visualize different data around them. But we also do a lot of cadaver studies, in this case, by superimposing on the patient. So what you see on the head of them, basically the HoloLens, which now is HoloLens 2 or which with more functionality, they include a lot of AI. That's really thanks to a lot of machine learning, in particular HoloLens 2 actually now, which is able to track your hands, track your position, your head, all with AI. So what we decided to do for the first time, this is also recent, is actually to also enable the C-arm and X-ray C-arm with the same HoloLens. It's funny to have a head-mounted display on an X-ray system, but the idea is that we want to have the same intelligence in terms of tracking and localization. So what we do is that once we will register this intelligent localization system with the X-ray system, and now from that point on, what would happen is that you can work in an environment where X-ray and optics are in the same world. So this is what we call the flying frustums, which means that as soon as you take an X-ray, you can see the geometry of the X-ray that you took. And therefore, you can actually take your X-ray and bring it on the patient because you know at which position the X-ray source was and the detector was. So now this allows a set of new applications. So we can actually do the acquisition of a whole surgery and then review what the acquisition was done from each point of view and how this whole thing was done during a whole surgery. So you can fully imagine that this can be also the case for angio. And also some of the other applications is to relocalize or reposition your C-arm. So once you take a position, now the assistant can see what was that position that you want to go to and can actually localize or reposition the C-arm. So these are a lot of applications. What is in the backbone of all this is AI. It would have not been possible to do all this connection between the imaging modality, the visualization, the localization inside the operating room, if we did not have this AI running in real time in the background. This is Dr. Osgood. He has these two X-rays that he had taken. Now these are the two frustums that he puts around the patient. And now he can localize. As he puts his drill, he can see where his drill would end up inside the patient. And then actually if he can see when he puts a prosthesis inside the body, where that would happen, where would it be located within the anatomy. And he can do an intra-operative planning, and then his next step would be to go ahead and actually say, I want to reach this target inside the anatomy. This is my entry point. You will see that he is defining those based on two X-rays. And then he goes back and looks at the patient, and now he can see exactly where those frustums are, where the line that he had defined to attack would be. And now he positions first the virtual drill, and you will see in a second he also takes a real drill, and then he starts to localize the real drill compared to his virtual drill. So this is all in the Johns Hopkins trauma department together with Greg Osgood and Alex Johnson. But everything you see here, the backbone, which is for them looks like complete magic now from A to Z, we are able to do that because in the backbone we have machine learning running on both now on the X-ray system and on the computer vision. So now the second part of the talk would completely focus on AI, and I talk a little bit about the challenges and how bring those AI solutions. So what you saw there was a lot of clinical applications that is very close to my heart. But in radiology, everybody is expecting machine learning to make a huge impact. And most of the reason is actually the fact that the data is overwhelming, and the radiologists only have a few minutes. I always give example of my wife. I'm a computer scientist, and my wife is a dermatologist. And about 10 years ago, 15 years ago, I asked her, when we were all talking about this patient card with all the information, I told her, if a patient comes to you and has a card, and in that card you have all the information of the patient from the birth up to now with everything, would you appreciate that? And her answer was, oh, definitely not. And I was very surprised, but then she told me, I'm still having only 3 minutes to 5 minutes with every patient. You give me millions of pieces of information and increase my responsibility to a maximum, but you don't give me 10 times more time. So it's not very helpful. Then I told her, okay, if you start making a diagnostics, and then from that card, from that data, we can extract the right information, only the relevant information, and show it to you. She told me, now you are talking. Now this is something I can consider. And this is only possible from my point of view now with machine learning, where also we can fight, I'm pushing something which makes it, that we can actually go for reducing the workloads. I would never consider, from my point of view, at least in the next 10, 20 years, AI replacing medical doctors. This is a myth which I think is completely wrong. It would reduce their workload. It would increase their common agreement. It would decrease the rate of error. And I would say this is going to be a super help for doctors and radiologists, and not something that would be able to replace them. So at the chair, also we have a strong group, which was actually through the years built partially by Professor Matthews, who is now here, but until a few years ago, she was with us. So we have a group of machine learning and experts which are sitting I call them the fundamental group that are working, in that case, on machine learning and application of it into the medical field. And some of the work that we did in that, and you can see that each of them, thanks to this machine learning, are beating the state of art currently. So the one which got an award at MIR conference in Switzerland was increasing the accuracy of real-time tracking of catheters. The second one was increasing the score in classifying femur fractions. We also did work on liver tumor classification or early detection of the diabetic retinopathy. Then there are a series of work that come into the game together with our on the neuroradiology department, Benedict Wissler in particular, where we started to also look at the tumor segmentation, lesion segmentation in brain MR. I show you later also detection of anomaly in those cases. And also in case of left atrium segmentation in cardiac ultrasound. So in all these cases, in the last, I would say, few years, not only us, I saw also that in your conference there are at least 8 or 9 or 10 papers which would be presented, a few of them this morning, on machine learning and deep learning for vascular segmentation in MR, for flow estimation, for a lot of applications that has started to, all the communities, I would say, have started to use this huge mathematical powerful machine that allows us to model more complex nonlinear phenomena with nonlinear functions which have tens of thousands of parameters that we could also estimate and go. Or we can do sometimes things that look like magic that I would say a few years ago was unthinkable. One of the work in that direction, now we have more recent work in this direction will be presented in MICAI. This was in MICAI 2016, where we decided when a radiologist looks at an X-ray, then the radiologist usually can see 3D. Because of the knowledge they have about anatomy, because the fact that the ribs are in front and the spine is in the back, you can actually eliminate them as you are looking at an X-ray and focus on deformable anatomy, for example, lung or other anatomy that is of interest to you. So the question was, with machine learning, can we do the same thing with an X-ray image? Can I decompose one single X-ray image in 3 layers of, front with ribs, back with ribs and spine, and in the middle with all my deformable anatomy? And the answer is it's possible. Definitely it's possible. The only thing you have to do, in this case, we are a little bit lucky, because if you have a few CTs, then thanks to the possibility of generating digitally reconstructed radiographs, you can now generate many, many data in which you first generate your projection data, then you decompose your CT into your 3 layers, and then you generate tens of thousands of views of each layer. So for every X-ray view, you generate a view of the first layer, second layer, and third layer. And the system starts to learn. And as you do that, we did it only with 5 patient CT, but also in this case, over 100,000 X-rays that we generated. And then we were able to actually take one single X-ray and get rid of the ribs in front and back, and only have a clean image of the deformable anatomy in between. So it was very interesting. This was also one of the first experience in X-ray for Shadi Al-Barkuni, one of our senior guys now on deep learning, and we had a discussion. He, like any excited scientist, he tried to apply that to other parts of the body, and it was very difficult to make this application. The reason is that machine learning is not going to do magic. It's just going to compute more powerful, it has a more powerful computation. So in this case, my guess, we have never tested it, is that if there is a nodule in one of the ribs, the nodule will be pushed into the lung. Because during our training, we had patients with healthy ribs and both in front and back. So the system started to learn, like actually a radiologist, that there is a nice shape of ribs, and then the Hounsfield unit associated to those anatomies are also in a given range, so it could gradually find a function to get rid of them. But now if in your training set you never had a rib with a tumor in it, the system has no way of learning that these ribs can also have things, and then of course it will push it back into the anatomy. So we have to be very careful in this case. For example, we will talk about it if you want to go to certification or etc. What was amazing here is that actually we also use this for some diagnostic imaging purposes. And by doing the cleaning of this front and back ribs in these images automatically, the rate of success of the CAD system, of computer-aided diagnostic system, increased by about 6%. So it's really very, very useful, but you have to be very careful because the data the system is as good as your data and as what it learns based on. Then we did the QuickNet. Now the story about this one, how many minutes do I have? Because I know we got lost about 5 minutes, so I'm trying to. Okay, I take it 5. So basically, QuickNet was a lesson we learned, is that something people started to think that machine learning is, I put all my data and then the system does magic. And from my point of view, this is completely wrong. We have hundreds of years of science, so basically we have to use that in order to reduce both our dependency on the defaults of our data and also make our system take advantage of everything we learned during the years. So in this case, there was a software at Harvard Medical School called FreeSurfer, which was developed over 20 years, where they were doing automatic segmentation of the brain. The quality was okay, not always perfect, but it was good. So what we started is that we took thousands of data of the patient automatically from the web. We ran it through the FreeSurfer automatically, and we used the data for training first our network. So what was happening was, since already our network at the end of this training was better than FreeSurfer, only because it was aggregating over tens of thousands of data. Once we did that, then we took the final network that we had trained now, and we gave it a very limited number of better segmented manual segmentation of the brain, about 500 of them. And now suddenly the network was beating systematically the FreeSurfer all over. And the FreeSurfer team came to us in MICA 2017 in Montreal, and they really loved it. They said, okay, this is great because you're using our work to train your network, to pass the knowledge that we have into the network. The same thing now we are doing in X-ray. For example, we have a new DRR generation where the digitally reconstruction generation process is not all learned based on images, but rather based on physics. But where we were trying to simulate the noise with Monte Carlo in the past, now we are trying it to do better with a network. So this was the power of showing the data, and again, going around the problem of annotation by using the crowdsourcing, in this case by Shadi Al-Barkuni. I go a little bit faster over it. And I try to actually summarize. One of the major issues is actually annotation, as you know. And one of the idea is to do weakly supervised systems. In this case, we could also get to the web, but as soon as you get weakly supervised data, you have to be extremely careful to not take wrong data. So there is a whole process behind it to evaluate whether the data that you are taking is correct. Now, in that sense, I want to mention something because I try to wrap up in 1 minute. Because something which is happening, and we were discussing it actually yesterday also, is the data is becoming more and more valuable. So we have this also issue that the clinicians in the hospitals, they start to share less and less their data, thinking that this is a gold mine, I don't want to share it. Now, both our group and many groups, one of the active one is also King's College London, are moving towards federated learning. In federated learning means that each of the hospitals learns with their own data, and then what is shared is the model, not the data. Now, the problem there is very similar to this case. That's why I'm bringing it up. You want to make sure that the training done at one hospital with their annotation is valid enough that it's not going to mess up everything you learned by giving you outliers. So in that case, you need to have automatic systems that look at that model and with some of the data that you have as ground truth, evaluates how that model is compatible to the model that you aggregated now. And a lot of problems that here we have the weekly supervised would happen there. So I will go very, very fast now. So basically, I just wanted at the end to tell you there is this problem of going from pure research into commercialization in case of AI, when you use AI. And the most difficult part, from my point of view, for AI solutions, which are based on clinical data, is all the phases you see in the middle. I can discuss with you about every of them. How to do the standardization and benchmarking, how to do the certification, how to integrate it into the workflow, and et cetera, in order to do a commercialization. And what we have started in Munich, and I hope that we can expand it. Now we are talking to Netherlands and also Imperial College London, is to have a platform where we can actually have on one side the hospitals and the academic, and on the other side the companies, and then in this platform being able to organize this both data processing, analysis, validation, certification, what I was talking about, evaluating the data, explainability, the fact that we could actually not only have a magic boxes, but boxes that we can explain. Thanks a lot. I'm finished. Thank you very much for time. I'm very sorry that it was too short and too fast, but I'm here during the whole day and we can discuss a lot about all these issues. Thank you.